Hello class, today we're going to focus on algebraic representation of vectors. We have been working with geometric representation of vectors, and I just want to refresh us on that we are using arrows that go from tail head, let's label this the U vector, and another one here, tail head, is our V vector, and we worked on how to use these and create other vectors like the addition vector here. I'm going to undo that and try to make it a little bit straighter. Being our V, oh sorry, not V. Let's go with W vector here. And that's our representation for geometric. Now, we can actually also represent this in algebraic terms. Okay, so let's try that out. Get rid of this. Alright, so we're given 2 points. Notice these are points, not vectors. If they were vectors, they'd have arrows. So these are points, A and B. Express the vector AB in component form. We'll go over what component form means in a moment, but let's set up our grid because we need to graph this. So I'm going to try to do a straight line here, and I'm going to try to do tick marks that are equidistant apart. Feel free to use graph paper to not make your life difficult here. And I'm going to say the first one is, let's do blue for 1, 2. This is A. And I'm knowing that in blue. And this one's going to be green for B, 3, negative 1. So remember, these are 2 different points. If we're actually going to try and get the vector for this, well, we have to look at how many steps do we have to go downwards. So we have to go 1, 2, 3, and then 1, 2 over. So we could just say what is the component vector, or well, I should say this is our graphical vector for that, right? Or geometric representation for that. But we want to do it in component form. Component form refers to the way you would talk about it as if this vector, the vector from here to here, we're starting as if it was starting from the origin. So there's actually a really easy way of writing it. If you're ever dealing with a vector that's not starting from the origin, you use this as your new origin. So the way we write that is simply by saying we have vector AB, and that's going to be equal to the difference of the second point, x, the second x minus the first x, comma, the second y minus the first y. And if we put that into practice here, we have the second x, which is 3 minus 1, comma, the second y, which is negative 1 minus 2. We get 2, negative 3. So let's compare to what we see there. If I were to draw this out, connect the dots of the geometric representation, do I have this motion of over 2 down 3 because of the negative? So are we over 2? 1, 2. Yes, we are. Are we down 3? 1, 2, 3. Yes, we are. Perfect. So that is our vector. If we wanted to show it from the origin, we simply have to go over 2. So 1, 2, and down 3. So it actually comes down to here if it was from the origin, AB. So I note all of this because the vector, without me drawing this arrow, connecting the dots, saying that AB is equal to 2, negative 3, already states that that is a vector, and it goes over 2, down 3. Alright, for the next question, we're going to say for part B, we're finding the magnitude of vector AB. So how do we find the magnitude? This is actually fairly simple. What we're going to do is simply take the component form and put it into Pythagorean's theorem. So x squared plus y squared, and take the square root of the whole thing. So I'm going to use green for this. So this is going to be equal to, write out this formula to state that we're going to have, and you can actually plug in, this is x2 minus x1 squared plus y2 minus y1 squared. And you may have seen this before. If you made the connection, kudos to you. So let's continue it and plug these in. I'll do this in red again, and maybe I should have done blue. I'll change that one to blue. Is equal to, and now we're just taking the square root of 2 squared plus negative 3. Almost got tripped up there. Squared. Make sure you square that negative 2 as well, I should say. And 4 plus 9, you're going to get equals, it's going to be root 13. So that's going to be our answer for this one. I'm going to change this one up. Let me just erase it and just make it blue for our notes. The magnitude measure of vector AB. And there you have it. So this was the beginning of our algebraic representation of vectors. Let's go further with other operations and just put them in terms of coordinates. So for our vector operations with coordinates, we have 3 different types here. We have vector addition, vector subtraction, and scalar multiplication. I'll talk about all 3 slowly, but please take a moment to try and copy this down. Okay, going forward, vector addition, I'm going to walk us through. We have 2 vectors, v and u. If we add them together, well, we're basing it on these coordinates here, or the component form, which is saying that this is a, b, and c, d. Well, we're going to take this individual a and add it to c here. They're both within the same dimension, so we have a plus c here and b plus d here. So this is our, let's say, our x's, and these are our y's. Doesn't have to be those, and that's why I wrote them as a, b, c, d. Alright, moving on. So we have vector subtraction, and this is where you have a negative vector. So if you have a negative vector, even though you have the same component form, right, you're taking this negative and you have to distribute it to both the c and the d, because now instead of adding them, you're going to get subtraction. A minus c, comma, b minus d. And last but not least, we have scalar multiplication. And I say scalar because in this case we're only multiplying the magnitude of the vector, aka doing nothing else to the direction here. So here we have k multiplied a and b, which distributes here and here to become ka and kb. Forgot my parentheses around there. So let's test these ideas out. So for this example, we're given 2 different vectors, u and v here. This one here is the component form of 1, negative 3, and this one is the component form of 2, 5. So we're going to do all 3 of these operations, u plus v, u minus v, and this one's going to have the scalar multiplication plus the vector subtraction. So give these a go, and we'll walk through them together in just a moment. Okay, so remember a reminder that when we have u plus v, vectors u plus v, we're going to take our representative ones in the x dimension for it. Let's say we're going to have 1 plus 2, comma, negative 3 plus 5. Now, reminder, the reason why, and I want to make sure of this misconception, that we're not going x2 minus x1 here because that's just finding your component form. So that's finding these already, these vectors in component form. These are just taking the sum of this part and this part. So please keep that in mind. You might be making that mistake in your work. But in this case, you're going to get 3, and this is going to be simply 2. So you should have this component vector of u plus v equaling 3 comma 2. Off to the next one. So in this case, we're going to do something similar for the vector subtraction. 1 minus 2, comma, negative 3 minus 5. And that's going to simply be, comma, parentheses, undo. We have negative 1, and this is going to be minus 8. And that's going to be our component for the vector operation of vector u minus vector v. And now this one here. So take time to do this one, because first off, I would say that 2 u is going to make this a 2. I would actually probably do it already out, saying that this is going to be 2, and this is going to become negative 6. So this is now 2u. That's my vector, components for the vector. And this one's going to be minus, and this is going to be 3v. So that's going to be 6 and 15. So now, with that being said, I can continue the operations here to say this is going to be 2 minus 6, negative 6, minus 15. So you're going to get minus 4, and this is going to be negative 21. So I was going to move on to example 3, but we did the video did run way longer than I'd hoped for, so we're going to end up putting that as a second video, and you can catch that as the second video for algebraic representation of vectors. So we'll end it here, and see you there.